So let's have a slightly more complex situation for this chain rule thing. Suppose you have a vector h, and this vector h is a function of some other vector, let's say some other vector a. At the same time, the vector a is actually some other function, let's call it f2, of some matrix w. And you want to get the derivative of the vector h with respect to the matrix w. So in general, the vector h might be an n by 1 vector. The vector A might be, let's say, a k by 1 vector, and the matrix W might be let's say, an L by Q matrix, and you want to get dH by dW. Now we expect this quantity right here to be actually a tensor having dimensions of n by L by Q in 3 dimensions, because you have n components in this h vector, and so you expect this to happen like this. Okay, now of course you can also have the flattened version of this, and in this flattened version you only have a 2D array instead of a 3D tensor, and for this 2D array you will have n again but multiplied by this number as 1 dimension. So in my derivation right now I will write dH by dW to denote the 3D tensor, and for the flattened version of this, I'll write it as dH by dW flattened. So this is the derivative in the 3D tensor 4. Okay, so dH by dW. We expect this result to be something like dH by dA multiplied by some dA by dW, right? We expect something like that to be true. This is the chain rule. Of course, we have first to prove that the chain rule holds true for this complex situation, but we can at least expect something like that to be true and then validate this expectation. So in this situation, I have dH by dW as a tensor as n by L by Q 3D tensor. dH by dA, we are deriving a vector with respect to a vector, so this will be a Jacobian matrix having dimensions of n multiplied by k, because the vector A right here has dimensions of k multiplied by 1, so we have a k here. Now this derivative is a derivative of some vector with respect to some matrix W, and this will be a 3D tensor again having dimensions of k by the dimensions of the matrix, so k by L by Q. So if this equation holds true, we are multiplying a 2D matrix by a 3D tensor. And we don't really know how to perform such multiplication. This is the first time we try to multiply a 2D array by a 3D array. So how can we perform this multiplication? Well, actually there is a nice thing happening here. We have that this dimension is the same as this dimension, and so if the regular matrix multiplication rules hold true for this complex situation, then we expect the result to have dimensions equal to n by L by Q, which happens to be the correct thing we are expecting for the left hand side, but we still can't decide for sure how this matrix tensor multiplication can be defined. So how do we proceed? Now, whenever I face a problem like that, I decide to take a step back. So let's try to take a step back and get dH1 on its own, the differential dH1. For simplicity, let's assume that the vector h is a 2 by 1 vector, so h is equal to h1 and h2. The vector A is also a 2 by 1 vector, A1 and A2, and let's also assume that the matrix W is equal to W1, W2, W3, W4, and of course all the conclusions we reach will be easily generalizable to different dimensions, but for this specific case let's try to get dH1 and dH2, which combined together can be used to get this vector right here. So I'll try to get this vector right here in a different way other than performing this multiplication, and from this other way we will be able to tell how to perform this matrix tensor multiplication. Now dH1, this can be written as dH1 by dA1 multiplied by dA1 plus dH1 by dA2 multiplied by dA2. But I don't want dH1 in terms of the vector A. I want this in terms of the matrix W. So I can still expand this dA1 using those four terms inside the matrix W, because the vector A is some function of the matrix W. And so dA1 can be written as dA1 by dW1 multiplied by dW1 plus dA1 multiplied by dW2 multiplied by dW2 plus dA1 by dW3 multiplied by dW3 plus dA1 by dW4 multiplied by dW4. So this is dA1. We can write this as the dot product of two vectors, or as the multiplication of a row by a vector. This row can be written as dA1 by dW, but this is the flattened form multiplied by dW in the flattened form. So this is a row, this is a column. Remember that dW flattened in the flattened form is a column equal to dW1, dW2, dW3, and dW4, just like that. So what I mean here is dH1 can be written, let's take this, let's copy and let's paste right here. This can be written as dH1 by dA1, this is a scalar, multiplied by dA1 by dW in the flattened case. So this is a row, this is a row, this is a scalar, and this multiplied by dW flattened, which is a column, plus dH1 by dA2, which is again a scalar, multiplied by dA2 by dW in the flattened form, which is a row, and here I have dW flattened, which is a column. So now a row multiplied by a column will give you a scalar, and multiply this by a scalar. So you will have a scalar which is consistent with what we want here. dH1 is really a scalar quantity, just the change in the value of h1. So this is a scalar. Very well. Now we see that dWf is available here and here. So I can take this as a common factor, and I can say that dH1 by the dW flattened is equal to dH1 by dA1, dA1 by dW flattened, plus dH1 by dA2 multiplied by dA2 by dW flattened. So we have the derivative of a scalar with respect to a vector. Wf is a column vector, and this result will be a row vector. So we have this constant, or the scalar, multiplied by this row plus another scalar multiplied by another row. So this will give you a row which indeed matches what we expect right here. Now this right hand side can again be written as, here I can have dH1 by dA1 and dH1 by dA2 multiplied here by another matrix having those two rows. So dA1 by dW flattened and dA2 by dW flattened. Remember the row method of multiplication. We are having linear combination of rows. So this constant multiplied by the first row, which is this, plus this constant multiplied by the second row. So this is really very nice. dH1 by dW flattened is equal to this. Now similarly, dH2 by dW flattened will be equal to dH2 by dA1 as a constant, dH2 by dA2 as a constant, multiplied here by dA1 by dW flattened as a row. This is a row. Here I have dA2 by dW flattened as a row. Now let's group those into a vector. So I can say that dH as a vector by dW flattened, this is equal to dH1 by dW flattened and dH2 by dW flattened in a column vector like this. Now this is equal to, here I can have dH1 by dA1, dH1 by dA2, dH2 by dA1 and dH2 by dA2, and this right here is multiplied by this matrix having dA1 by dW flattened. Here I have dA2 by dW flattened. Okay, now what is this? This is really what we wanted in the first place. We wanted dH by dW, and we got dH by dW flattened, but we could easily transform this flattened version into the tensor version, because dH by dW flattened will really be something like this. We'll have here dH1 by dW1, dH1 by dW2, dH1 by dW3, and dH1 by dW4 for our specific example, and here I'll have dH2 by dW1, dH2 by dW2, and dH2 by dW3, dH2 by dW4. So this is the dH as a vector with respect to the flattened version of our matrix, but we can easily get this and transform it into a 3D tensor, having here one floor and having a second floor, just like the one we have created before. So we can transform this to be the dH by dW unflattened very easily. Very well, let's also look at those. This matrix right here is actually the Jacobian. This is dH by dA, dH as a vector by dA as a vector. So this is dH by dA, and now this is equal to dA as a vector by dW flattened. So this is another Jacobian having the derivative of the vector A with respect to the flattened version of our matrix W. So now this is really our new chain rule for this specific situation. dH by dW in the flattened form is equal to dH as a vector, here as a vector, here also this is a vector, by dA as a vector multiplied by dA as a vector divided by dW in the flattened form. So we wanted initially to do this multiplication. We had dH by dW as a tensor, we wanted this as a tensor, and we thought that this would be equal to dH by dA as a matrix multiplied by another 3D tensor dA by dW, just like that. This here had dimensions of n by L by Q, this had dimensions of n by K, and this had dimensions of K by L by Q, and we didn't know how to do this multiplication, this matrix tensor multiplication. Now the result we achieved tells us that to do this multiplication, we first flatten this matrix W in order to transform this into a 2D array, having dimensions of K as height and then L by Q as width. After that, we do the multiplication in the original regular way of matrix multiplication, and after that we will get dH by dW flattened. Now we can unflatten this quantity again in order to produce this 3D tensor having dimensions of n by L by Q. So in a visual form, if you have a matrix here having dimensions of n here by K in this direction, and you want to multiply this matrix by a tensor having dimensions of K as this first height, then having also here L, and in the third dimension you have a Q, so you have here the Q dimension, and this is a 3D tensor, and you want to perform this multiplication. The first thing to do is you flatten this third dimension and transform this cube into a rectangle having dimensions of K as height and L by Q as width, and then perform the multiplication and then unflatten things back if you want.